The recording is live and the microphone is on. On Monday's class, we introduced a new topic, the energy of a reaction, aka thermochemistry. On that topic, we learned a little bit more about what is involved in understanding the energy of a reaction, in that every reaction will either release or absorb energy. However, most reactions will be negligible. In other words, most reactions, it will be not noticeable to the human eye. Some reactions do have a noticeable amount of energy associated with it, such that it does really lead to various changes in temperature. I think, for example, a heat pack and a cold pack, where in a heat pack, energy is overall released, and in a cold pack, energy is overall absorbed. This is accompanied by changes in temperature, where in an exothermic reaction, energy exits, such that the temperature rises, and in an endothermic, energy enters, such that the temperature decreases. I'm not going to go over too much detail, reviewing too much detail what we covered on Monday, but we're actually going to jump right into our next topic called acids and bases. And I actually like to call this topic acids and bases a spectrum. You'll understand where that word is coming from in just a few minutes. To understand a little bit more about acids and bases, we must first look at one of the earliest examples of an acid, water. Throughout history, water has exhibited characteristics of both an acid and a base. So to begin our understanding of acids and bases, we must first understand a little bit more about water. And again, throughout history, it has been known to exhibit both acidic and basic properties. This is what's known as amphoteric. Amphoteric describes a substance that has both properties, or rather can behave as both an acid and a base. Now, it's important to know that way back when this sort of terminology started coming up, when the transition was made from something like alchemy to hardcore chemistry, we didn't really have the appropriate words to describe what an acid and base is. So in fact, throughout history, there have been multiple definitions of an acid and a base, of which we're going to go over them right now. We're going to go over 3 definitions of an acid and a base. The very first definition was presented by a man named Arrhenius. And way back when Arrhenius was working with acids and bases, his only known example was that of water. So using water as our standard, Arrhenius actually defined an acid as an H plus producer and a base as an OH producer. This definition, as simple as it may be, did quite nicely encapsulate what we had seen with water. We knew that water is known to decay or decompose into its respective ions, H plus and OH minus. So if water is known to be both an acid and base, it must simultaneously produce hydrogens as well as OH ions. But as these things go, as science started developing, we started to discover more and more acids and bases. And all of a sudden, Arrhenius's definition was no longer valid. I'm not saying that it was wrong, but rather with how much chemistry had been developed, it had become a little bit left behind. A couple of his contemporaries, a duo by the name of Bronsted and Lowry, and they're German. This right here is an O with a line right through it. I don't remember what letter that's called in the German alphabet, but it's on purpose. Bronsted and Lowry, equipped with our new sets of acids and bases, revised the definition. They described acids as H plus donors In theory, these two terms, donor and producer, are similar. They are interchangeable. Bronsted kept the idea that acids were made or were a source of hydrogen ions. But as far as bases were concerned, Bronsted-Lowry, in fact, defined it as an H plus acceptor. You see, the OH producer definition was very useful because way back when, pretty much every chemical you worked with that was a base had OH. But as history progresses, new bases were discovered. I think, for example, NH3, ammonia. Ammonia clearly doesn't have an OH in it at all. So all of a sudden, Arrhenius's definition becomes slightly less correct. So Lowry then said, well, no matter what, we know that water acts as both an acid and a base. And based on the equation we had previously drawn, we can see how it is an H plus donor. So if Bronsted and Lowry's definition was indeed accurate, they could come up with a similar reaction for H plus accepting. Here, we have the reaction between water and an H plus. When they come together, they form H3O plus. And this was true. They were able to validate this reaction, were able to prove it, such that water has, in fact, two separate reactions. Number one, it splits up, donating or releasing a hydrogen ion. It can simultaneously accept a hydrogen ion to become H3O plus. Somewhat simultaneously, this time by a bunch of physicists, Lewis was able to make his own definition. Lewis described acids as electron pair acceptors and defined a base as electron pair donors. Now, in some way, shape, and form, all of these definitions are correct. Maybe one or two is more correct than the other, depending on context. Lewis, for example, his definition is mostly used in a physics class. For the purposes of Chem 1A, the definition we will consistently refer to is that of Bronsted and Lowry's. In this class, if we refer to an acid or a base, we call them either a proton donor or acceptor. Now that we have a little better understanding of what an acid and a base is, let's look at a specific example of a reaction between an acid and a base. Here we have the reaction between H2O, HCl, which results in H3O plus and Cl minus. Now, as we look at this reaction, it's important to note that technically speaking, you would not have been able to predict the products of this reaction. In fact, the reaction seen here doesn't nicely fit any of the archetypes that we've seen. Yes, you could argue that this looks like a double displacement, but it's not really a double displacement, is it? The H2O is simply grabbing onto the hydrogen and the chlorine is left alone, so it's not double displacement. This is all to say that you will never be asked to predict the products of an acid-base reaction, but you will need to know how to identify in the reaction which is the base and which is the acid. So to do that, we're going to look at our reactants on the left, and we're going to see how they end up on the product side and use that relationship to identify acid or base. Starting, for example, with H2O, we can clearly see that H2O becomes H3O plus. This is an example of water accepting a proton. Visually, that should be clear. Based on this logic alone, we can describe the H2O as a base. Remember that water is known to act as both an acid or a base, it's depending on the context. In this case, it's acting as a base. Now, the thing about acid-base reactions, just like redox, is that if you know one of the reactants is a base, the other reactant must be the acid. So without too much effort, once you identify water as base, you know that HCl is an acid. But let's prove it to ourselves. It starts HCl and it ends up Cl minus. Again, visually, what we can see here is that the HCl is donating a proton. You can even say it produces a proton, an H+. In other words, the acid donates its proton to the base that accepts it. So it is very much a symbiotic relationship. That hydrogen has to come from somewhere and it has to go somewhere. So that's it for identifying acid and base on the reactant side. You see, the truth is we can also agree on what the acid and base is on the product side as well. However, we want to make it clear that although there are acids and bases, some of them are on the reactant side, some of them are on the product side. To make that clear, we use the term conjugate. The term conjugate just loosely describes product. So when you see the word conjugate, literally think this is on the product side. We're going to use the exact same logic to identify which is an acid and a base here, but we're going to go in the opposite direction. Looking at H3O+, we see that it ends up H2O. This is a clear-cut case of the proton being donated or produced. With this in mind, H3O+ is therefore our conjugate acid. Remember here that the term conjugate literally means on the product side. So you don't even have to guess. These two products will have conjugate in their name, but the identification just depends on what's changed. Again, by simply identifying one of our chemicals as an acid, we immediately know that the other chemical is the base. Yet again, we can prove it for ourselves. It starts Cl minus, it ends up HCl. This is a case where the Cl minus has accepted a hydrogen ion, thus proving Cl minus is our base. This is a situation where water is acting as a base. Remember, like I said, you would never be asked to predict the products of an acid-base reaction, but you would be asked to identify which is the base, which is the acid, which is the conjugate acid, and which is the conjugate base. So let's see another reaction where water instead acts as an acid. This is the reaction between NH3 and water. Again, you would not be asked to predict the products. I would give them to you. We have NH4 plus and OH minus. Not writing the state symbols just to kind of increase clarity. Through the same code of logic, we can look at our chemicals one by one, starting with NH3, and we can see how it changes to the product side. Here, we see that the NH3 accepts a proton, literally grabs onto a proton, a hydrogen, and becomes NH4. This is what tells us that NH3 is our base. Since we've identified which reactant is a base, we know the other reactant must be an acid. Prove it to ourselves. We start H2O and we end up OH minus. Here, what we see is that the water is donating the hydrogen. On the product side, we can immediately write the word conjugate because we know conjugate means product side. And we apply the same logic. NH4 starts NH4 and it ends up NH3. This is a case where we've donated or produced a hydrogen. On the product side, we have a conjugate acid, and immediately we know the OH is a conjugate base. So identifying an acid and a base in a reaction or based on a given reaction is just a matter of visually tracking those hydrogen atoms. Now, throughout this discussion, I've been kind of interchangeably calling the H plus ion a proton. So why do we call H plus a proton? Why is it just not H plus? Why not just hydrogen ion? Why are we allowed to call it a proton? Well, the answer is actually pretty simple. If we look at the standard hydrogen, straight from the periodic table, we can see that it has 1 electron, 1 proton, and of course, 0 neutrons. Don't forget where neutrons come from. Neutrons are mass minus number of protons. That's 1 minus 1 to give us 0. So the standard hydrogen possesses an electron, a proton, and no neutrons. If we were to look at H plus specifically, H plus, of course, means that we've lost an electron. So now we have 0 electrons. We still have the 1 proton. And of course, nothing happened to the neutrons. So that's still 0. We can therefore see from the breakdown that H plus is literally just 1 proton. For this reason, the two terms are used interchangeably. In fact, you more often will see people just say proton instead of H plus. Why? Because it's only a proton that exists. Now we're going to talk about acid and base strength. So the question we must ask ourselves with this topic is, how do we rank acids? I mean, a lot of us may know in our day-to-day language, we understand that some acids are stronger than others, some are weak. You've probably heard in television or movies that corrosive acid burned through stuff. But not every acid is that corrosive. Not every acid is going to burn through things. So how do we rank acids? Well, we remember our definition, which is that acids donate protons. So if every acid donates protons, then we can, in theory, measure how easily the acid will donate the proton. Remember, this all comes back to hydrogen ions, those protons. Everything in this topic pretty much revolves around that. And it is from this particular logic that the pH scale was developed. The pH scale is a literal scale from 0 to 14, 7 smack dab in the center. And is a numerical scale that allows us to classify the strength of acids. In fact, it's known that anything to the left of 7 is acidic, and anything to the right is basic. That number 7 is identified as neutral. Because occasionally, sometimes you'll have a pH of exactly 7. It's neither acidic nor basic. It's simply neutral. It is from this scale that we are able to classify and rank acids. In fact, over here on the far left at 0, we have our incredibly strong acids. Over here is going to be our strongest acids. Conversely, over on the far right, 14, we have our weakest acids. Now, earlier I mentioned that I view acidity and basicity as a spectrum. So notice that we haven't quite yet so far talked too much about ranking bases. The simple reason for that is because acidity and basicity is a spectrum, by talking about acids, we can talk about bases. What do I mean by that? Well, remember how I said on the right-hand side is our basic side? If we keep going right all the way to 14, we actually are going to have our strongest bases. And sort of intuitively, that should make sense. If acidity and basicity is a spectrum, then an incredibly weak acid is simultaneously an incredibly strong base. So by talking about acids, by ranking acids, we unintentionally also rank bases, such that over here on the far left, our super strong acids will also be our super weak bases. And all of this comes from the pH scale, a literal numerical scale from 0 to 14 that allows us to qualitatively and quantitatively describe acids, where the H from pH, of course, comes from H plus ions. There is also what's known as a pOH scale. Remember, let's go back to our definitions. Remember, one of the first definitions of an acid and a base was that an acid is an H plus donor, hence pH. And in the base, we had OHs. That's pOH. However, just through history, since that terminology has dropped out of the lexicon, pOH is not widely used. So we simply say it's dropped out of the lexicon. You'll probably find every once in a while a very, very rare circumstance of a person actually using pOH, but it just is deemed unnecessary. Why? Because the pH scale kind of tells us everything. If we know that something has a pH of 2, we can say, well, that's a really strong acid. It is simultaneously a weak base. So for that very simple reason alone, pOH is not something that we regularly measure. How exactly does the pH scale calculate pH? How to calculate pH? Well, first and foremost, the exact mathematical formula is pH is equal to negative log of the H plus concentration. And that P, that letter P, literally means negative log. So it is meant to be read as the negative log of the H plus concentration. P is identical to the function of negative log. Now, let's bring out our calculators. I want us all to be able to identify where that log function is on our calculator. It's normally right near the 10 to the option or the exponent option. It will literally say log on your calculator. Please try to find it. On the scientific calculator app I have, it's over here by the number pad. It's just log. Since we now know what the formula is to calculate pH, we may sometimes have to find pOH. Although it has dropped out of the lexicon, or rather in our conversations, it is still a useful quantity to measure, pOH. And just like pH, there is a formula where, again, P literally means negative log. So pOH is negative log of the OH concentration. Remember, those square brackets literally mean concentration or molarity. Since we now know how to go from H plus to pH, it becomes important to know the opposite. In other words, how do we get H plus from pH? H plus is equal to 10 to the negative pH. Where does this 10 come from? Well, it is quite literally the opposite of log. Just as how we would say the opposite of addition is subtraction, just as we would say the opposite of multiplication is divide, the opposite of log is 10 to the, where of course the negative symbol is maintained in the exponent. By the same code of logic, we can also calculate the OH concentration using 10 to the negative pOH. Two more useful formulae to know, which is that the sum of pH and pOH will be equal to 14. And the product of the H plus concentration and the OH concentration is equal to 1 times 10 to the negative 14. These are the 6 primary equations that you will be using to calculate pH or any other value associated with it. You will be given these formulae as part of your reference sheet on the next exam. You do not need to memorize them. They will be given to you. So let's take a second to try a sample question and see how we would use this in theory. The question simply says, calculate the pH of a substance where the H plus concentration is equal to 0.0075 molarity. All right, so we just look at our given formulae, our 6 formulae. There should be one popping out to you as the one we would use. Obviously, we wouldn't use any of the ones with OH simply because it's not included. Looking at our options up here, if we want to calculate pH, we just take the negative log of the H plus concentration. This is now pH is equal to negative log of the H plus concentration, which is equal to negative log of 0.0075. And when we put this in our calculator, negative log of 0.0075, we get a pH of approximately 2.1. pH is typically written to 1 decimal place, and pH is unitless. But traditionally, we write pH to 1 decimal place, and the value of pH is unitless. So you would simply say the pH is 2.1, full stop. This is a pretty simple one. Let's try another. This one says, calculate the pOH of a substance where the H plus concentration is equal to, let's say, 0.0092 molarity. One of the immediate things you should notice with this question is the fact that I'm asking you for pOH, OH, hydroxide, yet I've actually given you the H plus concentration. If we look at the formulae that we have, there is actually no direct formula that relates pOH and the H plus concentration. There is no single equation that relates the two, but there are multiple. What do I mean by that? Well, see, I have the H plus concentration. In theory, I can use it to calculate pH. Once I calculate pH, I can then use another equation to calculate pOH. Let's see what that looks like. First things first, we recognize that pH is equal to negative log of the H plus concentration. In this case, this is negative log of 0.0092. Putting this into our calculator, we get approximately 2.0. Remember, it's rounded to 1 decimal place. We're not done yet, though, because the question specifically asked for the pOH. No problem. One of the other equations we know is that pH plus pOH is equal to 14. With a quick rearrangement, we can say that pOH is equal to 14 minus pH. Recognize all I've done is I've just carried over the pH. Now it's become negative. This is now 14 minus 2 to give us 12.0. Just like pH, pOH is unitless and is traditionally written to 1 decimal place. And this question really encapsulates what I mean by acids and bases are a spectrum. Because as long as we know some information about the acidity, we can calculate or determine information about the basicity of it all. Let's try another one. What is the OH concentration of a substance if its H plus concentration is equal to 3.3 times 10 to the negative 4 molarity? All right, so no, we're no longer asking about P and pH or pOH. Now we're talking about concentrations. We're asked what is the OH concentration of a substance based on its H plus concentration. There are a couple ways you can go about this. The simplest way is identifying or remembering, well, we have an equation right here that relates H plus and OH minus concentration. The product of the two is always going to be equal to 1 times 10 to the negative 14. So we simply use that formula. H plus times the OH concentration is equal to 1 times 10 to the negative 14. To get OH alone, we will divide both sides by H plus, which when canceled out, we can again write as OH concentration is equal to 1 times 10 to the negative 14 all over 3.3 times 10 to the negative 4. We can put this in our calculator. On top, we have 1 times 10 raised to the negative 14. On the bottom, we have 3.3 times 10 raised to the negative 4. We see here that we have 3.03. Let's make sure I wrote that number correctly. 3.03, it's repeating numbers, so that's fine. Times 10 to the negative 11, where since we're calculating concentration, there is a unit associated with it, aka molarity. So understanding the formulae and how they relate to one another, the different ways you can use them to calculate effectively the same information, will be paramount for your next exam. Like I said, you will not need to memorize these equations. They will be given to you. Now, beyond calculations, we can also predict whether or not an acid or a base is strong or weak. We're going to draw another table. We're going to be looking at examples of both strong and weak, examples of acids and bases. Examples of strong acids include HCl, HBr, HI, HNO3, H2SO4, and HClO4. Some examples of weak acids include CH3COOH, H2CO3, and H3PO4. Now, in general, I am expecting you to know this table. I may ask you on an exam to identify the following options as either a strong or a weak acid. So you will need to either memorize this table or just really learn it. Typically, the question comes up is, what's the rhyme or reason? Is there something we can use to predict a trend? And the truth is, I'm sure there are resources either out there online that suggest there is a trend. But to be quite honest, I haven't seen a perfect 100% trend. I've seen students in the past say, well, I've noticed that the strong acids only have one hydrogen versus the weak acids have multiple. To that, I say, well, look at H2SO4. H2SO4 is actually one of the strongest acids known, and it has multiple hydrogens. So that logic doesn't quite work 100% of the time. Works like 90% of the time, but not 100. Examples of bases, strong bases, include group 1 or 2 hydroxides. What does that mean? Well, we mean hydroxides with an element from group 1, such as lithium hydroxide, or from group 2, calcium hydroxide, where, of course, hydroxide is one of your polyatomic ions, And if it's attached to either a group 1 or group 2 metal, it is a strong base. Examples of weak bases include NH3 and most metal hydroxides. Not in group 1 or 2. Example of that is aluminum hydroxide. Aluminum is in group 13, so not 1 or 2. So it is described as a weak base. So like I said, you will need to commit this chart to memory. I could ask you on an exam to identify which of the following are strong or weak. And although there are some patterns, it doesn't work 100% of the time, but still useful to know nonetheless. Something you might notice here in the case of strong acids is HCl, HBr, and HI. This is hydrogen attached to a halogen, aka group 17. A common question that comes up is, what about HF? HF is notoriously very dangerous to work with in a lab setting. As a result, we don't really include it in our teaching curriculum. I think you actually need to be trained on how to safely handle HF specifically. So it's not something that we will regularly encounter in this class or in lab. I don't even think you get to work with it in 1B either. I think that's something for OChem. Do we have any questions so far on the nature of acids and bases? Okay. Now, I would like to talk about titrations. This topic is one you should pay careful attention to because today in lab, you will be performing a titration. So we want to spend some time understanding the theory behind it, why we use it, and how we follow along in lab. Titration is an experimental technique used to determine the concentration of an acid or base using the known concentration of another acid or base. A lot of this wording should trigger a memory of a topic for you, using information about one chemical to calculate or determine information about another chemical. Starts with S, ends with stoichiometry. Titration are experiments that exploit stoichiometry. AKA the relationship between one chemical and another. But notice that we're specifically working with acids and bases. And of course, acids and bases, we can measure them via pH. Now, titration experiments are usually indicated with color changes. In other words, we measure the pH by way of color changes. So it's a very visual experiment. In fact, today you're going to be making a faint pink solution. Let's talk a little bit about what that looks like. Let's take the reaction between sodium hydroxide and water. I'm sorry, not water, HCl. When these two come together, they react to form sodium chloride and water. You should be able to identify, based on the chart we just went over, between the reactants, which one is an acid, which one is a base. HCl, of course, is our acid, and NaOH is our base. Right now, we're not too concerned whether they're strong or weak. We just know that one is an acid, one is a base. Since we know the nature of their acidity and basicity, we can also make a concomitant prediction. We know that acids have a pH of less than 7, and bases have a pH greater than 7. So we are joining two chemicals that on the pH scale are on completely opposite ends. And when they react, they form, number one, a salt, sodium chloride, and water. Now, of course, a salt is neither an acid nor a base, so you can't quite measure it easily. But water is known to have a pH that should be pretty damn close to 7. Maybe sometimes you might see 7.1 or 6.9, but it should be pretty damn close to 7. So what we have here is a situation where we have two chemical compounds on opposite ends of the pH scale coming together, and by the end, the pH sort of balances out to somewhere close to 7. Titration is marked by the fact that we know the concentration of one of the chemicals, and we don't know the concentration of the other chemical. For the purposes of this example, I will tell us that we know that the concentration of sodium hydroxide is 0.0982. So you go to the store, or the lab manager goes and makes this for you, and you're like, okay, I know that the concentration of sodium hydroxide is 0.0982. I don't know the concentration of the HCl. I don't know that. Now, how does this experiment look like? So I'm going to draw something really quickly. Give me a second. Here we have a very, very simple illustration of the experimental setup. On top, This top glassware is known as a burette. And of course, we all should recognize that bottom one right there as a flask. In the burette is our sodium hydroxide. And that is not arbitrarily in the burette. What's in the burette is a chemical whose concentration we know. In this case, 0.0982. So the burette traditionally houses the chemical whose concentration we know with a high amount of certainty. The flask, on the other hand, contains our chemical of unknown concentration. That is how we know that the HCl will be found in the flask. And of course, the sodium hydroxide is in the burette. Recognize that depending on the reaction, depending on the experiment, you might know one or the other. So I don't want you to believe it will always be sodium hydroxide in the burette. It's the compound you know. What else is in the flask? Okay, well, we just said that in the flask is HCl. We know that HCl, of course, is aqueous, which traditionally means that we had to dissolve it in water. So there's water in the flask as well. And remember how I said that these changes are marked by color changes? In the flask, we also have what's known as an indicator. And the indicator is just a chemical that changes color depending on pH. The one you will be using today is known as phenolphthalein. It does not participate in the reaction. It does not contribute electrons or anything else. It is simply an indicator that changes color. In fact, phenolphthalein is clear, and when neutral, turns faint pink. There are many, many indicators because all they're serving is a visual indicator, literally indicator, that the pH has changed. In today's experiment, what you would do is that you would add sodium hydroxide until the solution turns faint pink. And by that time, what you would say is that the solution turned pink, that faint pink, after, let's say, 22.5 milliliters of sodium hydroxide. All right. Let's try to understand what we've done so far, what we're trying to do here. We are literally forcing a reaction between hydrogen, HCl, and sodium hydroxide. But this time, we're more interested in pH, and we want to calculate the concentration. So we fill up our burette with our known concentration, just the known, nothing else is in it. And we fill up our flask with our unknown chemical. In this case, the chemical, water, as well as the color indicator. You would open the burette and you would drip sodium hydroxide through. Over the course of time, the volume of sodium hydroxide decreases and the flask turns light pink. And you say, all right, I actually used 22.5 milliliters of sodium hydroxide. With that simple experiment of running the reaction and determining how much sodium hydroxide you need, waiting for the color change, we basically have everything we need to complete this. In other words, if I were to put this experiment in the form of a question, I would write, it takes 22.5 milliliters of 0.982 molarity sodium hydroxide to completely react with 25 mils of HCl. Calculate the concentration of HCl. Reading it in the form of a question should be a lot easier for you to say, oh yeah, I know what to do here. I'm being given information about one chemical, being asked information about another chemical. This is just the roadmap. We already have the equation on the previous page, right? We've already spent time on that. We already know it's 1 to 1 to 1. So we can write that we're trying to roadmap between sodium hydroxide and HCl. And we'll draw our boxes. Just give me a second. Let me just draw the roadmap in full. That will allow you guys some time to catch up with me as well. All right. So here is our general roadmap based on the written question. We can fill it in and determine what we're trying to solve. We're told some information about the sodium hydroxide. We're told some information about the HCl, and we're trying to calculate the concentration of HCl. We can plug these values into our roadmap, starting with the sodium hydro. Catherine, is that a hand? Did I forget a zero? I did forget a zero. Thank you for catching that, Catherine. Yeah, 1 second. Let me just fix this. Catherine pointed out that I just forgot to put a zero in my concentration. Thank you for that. I think that was Janelle. What's up? Yes. Now we're going to put this stuff into the roadmap. The sodium hydroxide, which color did I use over here? I used purple for sodium hydroxide. All right. Its molarity is 0.0982. And we're told that it takes 22.5 milliliters, so an immediate conversion to liters, since we're using it in the roadmap. We're told that it reacts with 25 mils of HCl. All right, so we're going to put that number in, 0.025, again, converting to liters. And in this case, what we're trying to find is our concentration. We, of course, already know that the ratio is 1 to 1. And the roadmap ahead becomes clear. We're going to go from volume to moles, mole ratio, moles to molarity. But recognize that we're doing something differently than normal. In every other roadmap usage, it's something in the box that we've been trying to find. For the first time, we're being asked to calculate something over the arrow, in this, what I've called the bus pass. Every other time I've given you the bus passes, or you've been able to calculate the molar mass. Now you're being asked to calculate the bus pass, the molarity. The process doesn't really change though. We're gonna go step 1, step 2, step 3. And make this a little smaller so I have space. Starting with step 1, which is going from volume to moles, specifically of sodium hydroxide. We know the formula, N is equal to molarity times volume, where molarity is 0.0982, and the volume we've already converted is 0.0225. .0982 times 0.0225. Looks like we have here, looks like a pretty small number. Let's put this in scientific notation. 2.21. Where do you see the sodium hydroxide first? Right, the step 1, we're doing this side first, and the volume we've been told is already 22.5, not 25, so not there just yet. 2.21 times 10 to the negative 3, it looks like. Mole. We, of course, can immediately write this number in, 2.21 times 10 to the negative 3. This is a very simple ratio, 1 to 1, so we can immediately write that number back. And then all that's left is step 3, which is going from moles to molarity, specifically of HCl. We know the general equation, N is equal to M times V. If we want to try to find molarity, we divide both sides by V, that becomes N over V. Think about where that came from. I just divided both sides by V. We know the number of moles is 2.21 times 10 to the negative 3. And we know the volume is 0.025. We'll put this in our calculator. 2.21 times 10 raised to the negative 3, all over 0.025, giving us a grand total of 0.0884. I'll write that whole thing out. 0.0884 molarity. This part should be familiar to you. When I give you the question exactly, and I tell you how much is needed, how much reacts, and what the concentration is. But today in lab, we will be performing the experiment that gives us that volume right here. Once you get the volume, the calculation is something you're used to. I'm spending time on this because the link between lab and lecture usually falls apart with this topic. On Monday's lecture with thermochemistry, we saw a marriage between experiment and theory. In other words, there was a chicken and egg situation in thermochemistry where we had to look at actual data and we could analyze it. But today, here, we're actually going to be performing experiments that give us the information we need to calculate concentration. And all of that comes from the very simple technique of titration, which is used with a color indicator. Do we have any questions? Okay. We're going to end lecture for today. We have lab in approximately 25 minutes, and it'll be based on this titration topic. I recommend, of course, take a break between now and lab, but kind of keep reading it over and over again so we understand what we're doing today. The most important thing I want you to understand is although the technique, the experimental technique is new, the theory behind it is familiar to you. If you have any questions, come talk to me now. Otherwise, I'll see you in about 25 minutes in 6:04.